So now we're well into we're past the intro part for the part 2 PDF, and I'll put the link up on a annotation here. Um, and we're about to invent a new kind of number, and we want to make sure that first of all the algebra, that's kind of the most basic aspect of it, works. And one of the things we need to be able to do with it is solve the quadratic formula, solve quadratic equations. So just to be a little simpler, let's set a equals 1 in the standard formula, for a quadratic, ax squared plus bx plus c. And let's review, or I want you to review, um, how you complete the square and solve that to derive the quadratic formula. And we just want to see what kind of uh, things we have to be careful about. What kind of algebraic rules must be true if this is supposed to work with x being some new kind of number that we invent. Okay, so let's do it. This is a good place to pause. But you rewrite this as x plus b over 2 quantity squared. That's x squared plus 2 times this plus this squared. Okay, so subtract that off because we don't really want that b squared over 4. The c is still there. That's equal to 0. Okay, so what have we just done? Well, we've assumed that you can take something plus something quantity squared and get the usual formula for it. That's the distributive law and the commutative law, and with the b over 2 in here, we've got like something times a half. That's going to be the associative law to make sure that you won't need all parentheses everywhere. Just in that one step, we've basically insisted that all of the usual rules of algebra or arithmetic, whatever you want to call it, for the real numbers should work for expressions involving this new kind of number. Okay, so then we move it over, and we get b squared over 4 minus c. Then we take the square root. Now this is, of course, the part that's going to be new. Oh, I don't really need the parentheses anymore. So that should be square root of b squared over 4 minus c. Now, when this is a real number, when this is non-negative, then this square root does exist as a real number, but we also get two answers. And we discussed in the previous video how we want to get two answers still, because we want to get two independent solutions to a second order differential equation. So we certainly want that kind of that aspect of square rooting to work, where as long as this is not 0, we want to get two answers. And then, of course, we subtract that over. And then we do a little more algebra, and that's going to involve really factoring out something, the 1/2. And so that's the reverse of the distributive law, so it's using the distributive law. And then b squared minus 4c. Okay, so there's a lot of algebra that's required to go from here to here. Getting a little bit past the screen here, sorry. And so the point is not so much this answer, it's that we better have all those rules of algebra. So what I want to point out in these next video or 2 or 3 is how we're going to be just absolutely forced at every stage to do what we do. We're not inventing something with any freedom whatsoever. When we invent something called the square root of minus 1, everything else is going to follow without any choice. And so in particular, we can't be very creative about the rules of algebra. We don't want to be. But certainly this forces us to define things in a certain way. The other thing is, notice that if this is going to be one of these new guys, the square root of a negative number, we're going to often be dealing with expressions of the form real number plus or minus square root of negative. And that's going to be the familiar kind of something plus something times I from complex numbers, if you are familiar with complex numbers. Okay, so that tells us what kind of expression to define. Oops, let's see, I don't want to waste that piece of paper. We're going to take a real number, and let's say u plus vi. Since I just used a and b for a different purpose, I think, or at least b, I'm going to use u and v. And we'll call that one object. And this is really important, that this is one object that has a real part and an imaginary part. And the whole thing, when we consider it as a unit, we'll use various letters for it, but z is a very complex, or very common name for a complex number. Okay, so now suppose we had two of these guys. Let's put subscripts here. So we need to figure out the rules of algebra here. z1 plus z2. Okay, so this is already on to problem 2, if you're following along on the PDF. There we go. Okay, we need to have a definition for that. And here again, we just don't have any choice. It's going to be forced on us what to define. We'd like to figure out, okay, we'd like to get it back in this form of real plus imaginary times I, okay, or this, I might as well address this right now. This guy, this real number is called the imaginary part of this complex number, even though it's not actually, even though it's a real number. And that can be a very confusing thing. Often people want the v1i to be the imaginary part, but for good reasons, this number, the coefficient in front of I, is the imaginary part. So if I use that terminology, that's exactly what I mean. Okay, I want this to be something plus something times I. And you should pause if you're at all unsure what that should be. It's forced on us by assuming that we can reshuffle this at will and then factor out an I, which is just the commutative and associative laws for addition and the distributive law for multiplication over addition. It's just going to be the real parts added together and the imaginary parts added together. Okay, so that has the advantage of being absolutely the simplest thing and pretty much what anybody would guess, but I want to point out really that it's forced on us. We're not really being creative here, unfortunately. Okay. All right. So the other thing to notice is even though we're doing algebra here, I want to bring the geometry back in as soon as possible, and the calculus as soon as possible too, but it's going to take a little while. Okay. This thing, this rule of here's a single quantity that has two real number pieces, and when I add two of those compound quantities, I add the first parts together and the second parts together, that's vector addition. Okay, so this is equivalent to the data of having like a vector. Just depends on what notation you like. Some people use angle brackets. Sometimes you would put in a column vector, but I don't think I'll bother to do that. This is the same data as in a vector because it has these two components. Well, that has a geometric interpretation. Woo, like that. Okay, so there's a very standard way to draw this, and again, if you're at all familiar with complex numbers, this is not anything new. That's to put 1 right here, so this would be 1 plus 0i, and to put I, naturally enough, in the other along the other axis orthogonal to that, and there's actually incredibly good reasons to make it orthogonal. Again, this is really forced on us. In case you were wondering, I'm slipping a genuine choice under the rug. That's just 0 plus 1i. So that's 1 comma 0, 0 comma 1. That really should go in this location and this location. And then here is going to be something like, ooh, it doesn't look like it has an integer. Maybe 1.5 plus 1.2i, something like that. Okay. So this already would suggest that we could draw complex numbers as points or arrows in the plane. Arrows are going to be more useful in a lot of ways, although they're both useful. And I'm going to sort of not worry about the distinction too much. Vectors in the plane, at any rate. And so that already suggested it because it has exactly the same information content. This gives an even stronger suggestion. Because really, the fundamental thing about vectors is not so much that they have a certain amount of information content, it's what you do with them, what the rules are to manipulate them. And adding vectors is exactly corresponding to this rule. That's really good evidence that this should be the right picture for complex numbers, the right geometry of complex numbers. Okay, so in the PDF, I suggest a few basic exercises, which you can totally skip if you really already know the answer, but just drawing a couple things and drawing their sum. And the punchline, so again, good time to pause, look at that, or just come up with some complex numbers on your own, add them up. What's the geometry? It's just the standard geometry of adding vectors, that if I have these two vectors, I draw a parallelogram, and the sum of these two vectors, or in other words, the sum of the complex number, let's say like z plus w, is just that arrow, and it makes a parallelogram. That's very, very naturally geometric. That's wonderful. Okay. There's even a little more sophisticated way. So what we'll do is let's fix z to be a single complex number, a fixed complex number, 2 plus I. So let's sketch that. 1, 2, I. And here's, okay, there's z equals 2 plus I. Okay. And now what I want to do is I want to take a whole bunch, oops, this is equals, a whole bunch of random complex numbers all over the complex plane and see what happens. What happens to w when I add z to it? Okay, so I'm going to take w and I'm going to replace it with the z plus w. And that's a function, or I could call it f of w, for example. If I wanted to, I could decorate it with like f sub z. Okay. What does that do geometrically? So instead of treating the two vectors, well, complex numbers, vectors, whatever, the two complex numbers on an equal footing, like here, I'm thinking of this as something that's creating a function, a transformation of the plane. So every arrow here, finally, I get to use a different color, although it's not going to show up very well. So here, this guy, okay, and you know what? I'm going to cheat a little bit, and I'm actually going to draw that as a point. And I'm going to think this is a point, something, and that's a good role for something that's sort of passive, being acted on. And an arrow is a good thing for the thing that's doing the action, that's creating the transformation. Okay, what's going to happen to this guy is going to be acted on by the green, and end up over here. What about this guy? Okay, well, if I had to draw the arrow, it'd be like this, and then I draw the parallelogram. But really, all it does is it slides this arrow to be parallel to itself and ends up here. Or in other words, these should be in green. All these blue points get moved by the same green arrow. So if I have a blue point down here, it gets moved by exactly that same green arrow to be a new blue point here. Okay, and so there's a motion of the plane created by this complex number. Okay, so this is a translation, to use a little bit of a fancy word, or like a shift, just a motion in one direction, fixed direction, fixed magnitude. And that's a really, really, really important interpretation of addition of vectors and the hence addition of complex numbers. So that's very, very cool. And then as an extra, I'm not going to do it. If you really want to check, as we go through these algebraic laws, you should check it. They really do satisfy all the rules of basic algebra, you know. Commutative law, associative law, distributive law, everything like that. Make sure that 0 plus 0I should be the 0, which means if you add it to something, it should get the same thing. You should check it if you're skeptical, if you're in a rigorous frame of mind. Okay, now let's look at multiplication. Okay, it's getting a little long here, but I mean, multiplication is kind of the more interesting thing. So let's at least start to look at multiplication. Okay, so this is number 3 on the PDF. Okay, so let's again take like u1 plus v1i and times u2 plus v2i. Okay, and we want to define multiplication. So as usual, we just put them next to each other to indicate multiplication. Okay, well, it should be some real part plus some imaginary part times I. Okay, and again, we have no choice here. Absolutely no choice. We insisted that the usual rules of algebra have to hold, or else we're going to be it's going to completely mess things up, and in particular will mess up the quadratic formula that was so important. So, u1, u2, well, that doesn't have any i's in it, so that definitely goes here. Not sure if you see any other reals, but let's leave a space. u1 plus v2, that's got an I, so I'll factor it out. u2 v1, and notice I'm not worrying about which way I write them because, of course, multiplication of real numbers is commutative. Okay. And then, v1, v2 times I. But I squared is minus 1. That's the whole point that drives this, is that I needed to have square roots of negatives, and I was, by definition, the square root of minus 1. So we're going to get minus v1, v2. That's pretty funky. So there are 2 real contributions and 2 imaginary. Among the 4, which is nice and symmetrical. Okay, and that minus sign just shows up in all kinds of funky places. Okay, but because it's I squared. Alrighty, so let's just do, that was part A. And again, whenever I dive into something, pause and make sure that you can see if you can do it yourself, as the PDF suggests. Let's just check one thing. I was trying to make a big point when I talked in a minute ago about vector addition and the fact that what really convinces us that these guys should be drawn as arrows or points in a plane is that the operation that we invented, the algebra, does correspond to what you do with vectors, and it does encode exactly the same geometry. Well, there's another piece of geometry that vectors encode, which is scalar multiplication. I can take an arrow in the plane and make it bigger or smaller or flip its direction opposite. Those are all just accomplished by multiplying by a real number. Well, that's a special case. It better be a special case of multiplying complex by a complex. Okay. And indeed, that's u1 u2 plus u1 v2I. It's exactly what happens when you multiply a scalar times a vector. When you take like 3 times the vector 5 minus 7, by definition, it's just 15 minus 21. It just multiplies each of those things by that fixed number. Okay, so that's our first hint. It's the less interesting part of the geometric meaning of complex multiplication, but it's certainly really significant. It means that multiplying by a real number, that's the real numbers, right? That scales. Okay, so multiplying a complex number by a real number just scales this complex number. Okay, so we can even put that in the context that we had before. Adding any fixed complex number to a bunch of different complex numbers produces a shift. That's the transformation induced by addition of a fixed complex number. Now we can say if this is like 7 or something, then 7 times a bunch of complex numbers is going to scale. Okay. And so, like if I have this complex number, this complex number, this complex number, and then I just multiply by 3, it's just going to scale everybody. Okay. Can't change the direction. But I wonder if other kinds of multiplication can change the direction. Very interesting question. Okay. So that's a good place to stop this video. And look at the PDF and see if you can go further without even starting the next video.